Example 172. Find the 95% prediction interval for the height of a woman given that she has a shoe size of 6. So let's be careful with the language here. A 95% prediction interval is not a confidence interval. A prediction interval is quite different. Well, I shouldn't say it's quite different. It is different. It's not quite different. They're actually pretty similar, but the difference is that prediction intervals are designed to predict literally in this case, the height of a specific woman given that she wears a shoe size of 6. That's much different than the confidence interval, which we did before, which talked about the average height, for example, of a woman who would, or for women, plural, that wear size 6 shoes. So a confidence interval would talk about the average height of women who wear size 6 shoes, while the prediction interval talks about the height of a specific woman. It's going to be harder to predict that height precisely, so as a result, we're going to have a wider interval to ensure that we capture a specific woman's height. So this is going to be reflected in our formula for the margin of error. A lot of the other steps will be almost the same as what we did before. Let's start with the first step that we did last time. We're going to need to redo that. The first step we're going to do is to come up with the model and then use the model to make a prediction about the shoe size they're talking about. So xp here, the x value that we're making our prediction at, is 6. So we're going to use that in our model. Our model is y hat equals to, remember it's beta naught hat plus beta 1 hat times x. And for us in this specific case, we have beta naught provided to us as 44.421 plus the slope, which is given as 2.617, and they're multiplying that times our x value, which of course is 6. Let's get that predicted, or our y hat value for the predicted x value of 6. So we'll have 44.421 plus 2.617 times 6. Alright, and when we're done, we get 60.123. So our model says that the person should be about 5 feet tall, right? Okay, from there, we're going to take that value and use it in the last step, step 4. But in the meantime, in between, we're going to have to go to our table to get our critical value. So we have t alpha divided by 2 here, t because the sample size is small. We'll have degrees of freedom n minus 2, right? Okay, so alpha divided by 2, if it's a 5% alpha value, since the confidence level is 95%, and if we divide that in half, we'll end up with t.025. And n minus 2, if you look at the problem here, we have 1, 2, 3, 4, 5 values, so n minus 2 will just be 3. Let's go to our t-table then and find that corresponding critical value. Okay, so we're looking in the 0.025 column, and we're going down to 3 degrees of freedom. We find the value 3.182. Okay, so we found the value 3.182. Alright, now that we have the critical value and we have our data from step 1, let's go on to step 3. Step 3 is to get the margin of error. That formula here is a little bit different than before. Before, we basically had a formula that was like this one, so let me write down what we have here first. It's t alpha divided by 2, s times the square root of, so everything up to this point is about the same actually as before. Before though, we had 1 over n first. Now we're going to have an extra value first. We're going to have 1 plus 1 over n. And then we'll have plus, the same, everything else is the same. It'll be xp minus x bar squared divided by the sum of squares for the x values. So all of that is our value. What's important about this is this. When you're doing a prediction interval, you could eliminate this quantity if you wanted to, just by making sure that your predicted x value is at your average x value, right? So x bar here is 7.1, it says. If we made xp 7.1, then these two would subtract to give you 0. This whole thing would drop out. In the previous confidence interval, then all that would have been left in this square root would have been 1 over n. And if you had a really large n, then this value would approximately go to 0, which would mean that you could then, as a product here, ensure that the overall error would be very tiny or close to 0. Which means that theoretically, in a confidence interval, you could get your prediction to be really precise. However, in this prediction interval, you'll never be able to get around the fact that there's some natural variation that's demonstrated or given by s, because no matter what you did, even if you had an n that was infinity and you would get that to go to 0, and even if you picked a x prediction value of x the same as x bar so that this cancels out to 0, you'd still have that 1 under the square root, and the square root of 1 times s would just give you s, and so you would not be able to reduce the error any lower than t alpha divided by 2 times s. And so as a result, you're always going to have a certain amount of error in your prediction. So a prediction interval can never give you the precise answer, right? It's always going to have or be subject to this natural error variation that occurs, and of course also subject to your critical value. Alright, so regardless of that difference, what it basically boils down to is that the prediction interval is wider than the confidence interval. And that should make sense because we're trying to predict the height for a specific woman as opposed to the average height, and that's a harder thing to do. Alright, let's enter the numbers in. We have everything we need for this. T alpha divided by 2 is 3.182. The S is given to us in the problem as 4.19. So 4.1924 times the square root of, and in this case the square root is going to be 1 plus 1 over. Remember that our n was 5, we took 2 away to get before to get 3, but it's 1/5 here. And then we'll have plus the xp, that's going to be 6 in our problem, minus the sample mean. The sample mean is given to us here as 7.1. And we'll square that and then divide by the value SSXX, which is 10.7 for this problem. Okay, let's see what that all gives us ultimately. So I have 3.182 times 4.1924 times the square root of 1 plus 1/5. I'm just going to do 1 divided by 5. You could also type in 0.2, right? Plus, use parentheses here, 6 minus 7.1, close the parenthesis, square, and then divide by 10.7. And then finally close up the other parenthesis. When you're done, you get an error here of 15.2865. I'm going to store that into my calculator so I have it for use in the next step. Alright, so the error here is pretty large. Let's go on though to the next step, the fourth and final one. The fourth and final step means you just take the y hat value that you calculated in step 1 and you subtract off the error, and then you do y hat plus the error. So in our problem, y hat was 60.123. We'll subtract off the error from that, and then we'll do 60.123, and we'll add the error to that. And that will ultimately give us our interval. So I have the error stored in our calculator. Of course, it's written right here above. Let's go ahead and work that out then. So we're going to do 60.123 minus the error, and then do the same thing, but this time plus the error. Alright, so our interval turns out to be, and this is going to be quite a wide interval here, it's 44.8 up to 75.4. That's in inches, right? So basically what we're saying is that we're 95% confident, right, that the woman who wears a size 6 shoe will be somewhere between 45 inches tall and 75 inches tall. Remember that 48 inches would be 4 feet, right? So of course this is saying that she's going to be somewhere between under 4 feet, and 75 inches is over 6 foot, which would of course be 72 inches. So we're saying she's somewhere between the heights, under 4 feet up to something greater than 6 feet, right? So this is not a very useful interval, in other words, right? I mean, I could probably have done that prediction for you without having all these numbers crunched, right? I mean, if you told me some girl has a shoe size of 6, I could say, well, that means her height's somewhere between, 4 feet and 6 feet. Well, I think that's pretty obvious. I think for most people, they would say you didn't need a lot of mathematics to figure that out. So what I've illustrated here is that you can form a prediction interval, but if you have a small sample size like we have, and you have a pretty large natural occurring error, the S value here is pretty large. If you combine those factors together and the fact that you're doing a prediction interval, your interval will generally be pretty wide. And when an interval is that wide, it's virtually useless. So we would obviously need to, in this case, give a larger sample size at least, maybe get an XP value that's closer to X bar. That will also help, And then finally, The other important factor, which we cannot control, is this S value. We can't make it smaller. That's not up to us. But if we could, do that, then it would be more helpful. That S value, remember, comes from the model's error. It's an estimate of the standard deviation of the error term, and that quantity, it has something to do with the model. If the model was better, obviously we'd have a better, S value. But of course, we can't control how good the model is. If we're using shoe size to predict heights, that's the error that we come up with. So anyways, that's the end of the problem. At least we know how to do the calculation. The results aren't wonderful, but at least we performed everything correctly.